Welcome to this video, where I take a look at section C of the first edition of Principia Mathematica. This section is titled Classes and Relations. As we see on page 92, Whitehead and Russell divide mathematical logic into three parts. 1. The calculus of propositions, which was dealt with in section A. 2. The calculus of classes, and 3. The calculus of relations. 2 and 3 are covered in this section, section C, which I'll be starting to cover in this video. In the previous sections, it could be easy to lose sight of what the aim of Principia Mathematica is, a reduction of mathematics to purely logical principles, since what was covered in those sections is not recognisably mathematics. Sections A and B have been quite intense on the logic side of things, but in section C, there is a definite shift towards some more recognisable form of mathematics. Nevertheless, the mathematics that we come to is almost certainly incomprehensible without some understanding of the previous logic sections. In this video, I'll take a look at chapters 20 and 21 from section C, which are titled General Theory of Classes and General Theory of Relations respectively. I'll cover chapters 22 to 25 in a separate video to try to keep the videos to a reasonable length. Most of this video will be concerned with classes rather than relations. It's important to note that the notion of classes given in Principia Mathematica has many parallels and similarities with the modern concept of set, but the notion of class, according to Whitehead and Russell, and the modern notion of set are not identical. At the time of writing Principia Mathematica, the notion of set or class was still very unclear, with different ideas emerging trying to escape the contradictions inherent in less formal, naive set theories. Indeed, it was only a couple of years before the first volume of Principia Mathematica was published that Zermelo gave his controversial axiomatization of set theory in 1908. Russell, of course, wasn't entirely convinced, and it probably didn't help that Russell was presumably trying to champion, to a certain degree, his theory of types as a suitable basis for set or class theory. Therefore, we have to accept that although the classes of Principia Mathematica have many of the same properties as sets, in the more modern sense, the classes of Principia Mathematica are ultimately a different kind of thing, and what we have come to see as usual properties of sets may at the time have not been so usual, and so there may be some surprising results from time to time, at least surprising from the modern perspective. On page 196 in the introduction to section 20 we see, the following theory of classes, although it provides a notation to represent them, avoids the assumption that there are such things as classes. This it does by merely defining propositions in whose expression the symbols representing classes occur, just as in section 14 we defined propositions containing descriptions. On page 60 we see, it should be observed that if we assume the existence of classes, the axiom of reducibility can be proved. And Whitehead and Russell go on to say, if we assume the existence of classes, the axiom of reducibility becomes unnecessary. The axiom of reducibility is therefore a smaller assumption than the assumption that there are classes. And finally on page 61, on the ground that it is always well to make the smallest assumption required for proving our theorems, we prefer the axiom of reducibility rather than the existence of classes. So Russell and Whitehead don't deny the existence of classes, but simply present a theory in which there is no need to assume the existence of classes, and where a smaller assumption can be made. Following the onslaught of sections A and B, section C will probably feel much more straightforward. A lot of the hard work has already been done in the previous two sections, which isn't to say that there isn't more hard work to come, but the intensity drops off, at least temporarily, in this section in my opinion. There are many omitted demonstrations in these sections, and I'd thoroughly recommend that you attempt to reconstruct some of these demonstrations yourself to get a better feel for how things are working. I've mentioned in a previous video that the hints given, whether the demonstration of a proposition is included or omitted, are often incomplete in many ways. That is, only the main or less obvious propositions that may be required for the demonstrations are referenced. Propositions from some of the early chapters, say chapters 1 to 5, are often not mentioned. By going through some of the demonstrations quite thoroughly, or reconstructing the omitted demonstrations, you can start to see this for yourself. You don't need to work through every single demonstration or write out every omitted demonstration. As I read through Principia Mathematica myself now, I'll check the odd demonstration here and there in detail, and I'll sometimes have a go at writing out a couple or a few omitted demonstrations, but generally I'm more interested in just getting my head around the various concepts and statements of propositions. Even fleshing out the details of the demonstrations that are included is incredibly difficult sometimes and very time-consuming. At this point in Principia Mathematica, Whitehead and Russell are often giving something resembling sketch proofs of the propositions. And I think it would be unfair to criticise Whitehead and Russell for leaving out some of the detail, since Principia Mathematica is already around 2,000 pages in length, with sketch proofs. So I dread to think how long Principia Mathematica would have been with complete demonstrations, whatever that might mean. Nevertheless, it's well to be aware of the extent certain details have been omitted, so that you're more prepared to fill in the gaps should the need arise. For example, the demonstration of proposition 20.11 gives a good idea of the main steps of the proof, but a complete demonstration would probably require a few more steps to be absolutely clear. We also have the demonstration of proposition 20.12 completely omitted. A few hints as to which propositions might be needed in the demonstration is all you're going to get from Whitehead and Russell for this proposition. I've recently uploaded a video looking in more detail at the famous proposition 54.43 from Principia Mathematica. In this video you can see an example of how I've taken the demonstration of that proposition and filled out some of the details by writing a more complete demonstration, in inverted commas, to try to show what filling out the details might look like in practice. In this video I won't be focusing too much on demonstrations though. I think I've said about as much as I really need to say about the style of demonstrations in Principia Mathematica in my earlier videos. If you are able to follow the demonstrations up to chapter 14, then the demonstrations in this chapter and subsequent chapters won't really be any more of a challenge to follow. I may touch briefly on a demonstration here and there, but I really want to focus on the notions and the ideas involved. So let's have a look at chapter 20, the general theory of classes. The view of classes that's taken in Principia Mathematica hinges on the concept of extensional function, as opposed to an intensional function. A function is said to be extensional when it depends only on the truth values of its arguments. On page 76 of the introduction we see, a function of a function is called extensional when its truth value with any argument is the same as with any formally equivalent argument. And on the same page we see, a function of a function is called intensional when it's not extensional, and I'll be saying more about this later in the video. It shouldn't be assumed that just because phi and psi are formally equivalent propositional functions, then f of phi and f of psi will automatically have identical truth values, since functions of functions fall into the two categories extensional functions and intensional functions. Some examples of extensional functions and intensional functions are provided on pages 76 and 77 of the introduction. However, when two functions are formally equivalent, then we can imagine them having something in common, and this something is what we might informally call their extension. The extension of a function is not formally defined in the system of Principia Mathematica and is only to be considered as a kind of informal object. As we'll see, it's the extension of a function that we regard as forming the class defined by that function. Thus, if a function of a function, f of phi, is extensional, we may informally view this function as saying something about the class determined by the function phi blank, or saying something about the extension of the function phi blank. On page 79 we see, it's convenient to regard an extensional function of a function as having for its argument not the function, but the class determined by the function. And just to be clear, it is extensional functions that we're concerned with in Principia Mathematica. On page 197 we read, the functions of functions with which mathematics is specially concerned are all extensional. Even though we may, for convenience, regard a function of a function as being a function of a class, the function is nevertheless still a function of a function, no matter what we dress it up as. On page 92 we see, classes and relations, like descriptions, are shown, in section C, to be incomplete symbols, and it's shown that a proposition which is grammatically about a class is to be regarded as really concerned with a propositional function and an apparent variable whose values are predicative propositional functions. On page 75, in the case of descriptions, it was possible to prove that they are incomplete symbols. In the case of classes, we do not know of any equally definite proof. It's not necessary for our purposes, however, to assert dogmatically that there are no such things as classes. It's only necessary for us to show that the incomplete symbols which we introduce as representatives of classes yield all the propositions for the sake of which classes might be thought essential. When this has been shown, the mere principle of economy of primitive ideas leads to the non-introduction of classes except as incomplete symbols. We also see on page 24, a class, which is the same as a manifold or aggregate, is all the objects satisfying some propositional function. If alpha is the class composed of the objects satisfying phi blank, we shall say that alpha is the class determined by phi blank. Every propositional function thus determines a class. Of course, it could be argued that since all of the objects satisfying phi blank form a class, then all of the objects not satisfying phi blank also form a class, and of course no object will be a member of both classes simultaneously. However, we may consider the objects which do not satisfy phi blank as being objects which do satisfy not phi blank, and so can still be considered as the extension of a propositional function. And therefore, a class in Principia Mathematica is the extension of some propositional function. On page 77 we read, when two functions are formally equivalent, we may say that they have the same extension. In this definition, we are close in agreement with usage. We do not assume that there is such a thing as an extension, we merely define the whole phrase having the same extension. Also on page 77, it's natural to regard the extension as an object called a class, which is supposed to be the subject of all the equivalent statements about various formally equivalent functions. The symbol used for a class is a symbol of the form z hat phi z, which can be read the z's which satisfy the propositional function phi blank, though of course it must be remembered that this is only an informal interpretation of this symbol, which is, as we've seen, an incomplete symbol. There are 5 properties that we require classes to satisfy. 1. Every propositional function must determine a class, which may be regarded as the collection of all the arguments satisfying the function in question. It must hold also when no arguments satisfy the function, i.e. the null class, must be just as good a class as any other. 2. Two propositional functions which are formally equivalent, i.e. such that any argument which satisfies either satisfies the other, must determine the same class. That is, a class must be something wholly determined by its membership. 3. Two propositional functions which determine the same class must be formally equivalent. 4. There must be classes of classes. And finally 5. It must be meaningless to suppose a class identical with one of its own members. And this final property is, of course, closely related to the vicious circle paradoxes, which Whitehead and Russell are keen to exclude from the system of Principia Mathematica. Whitehead and Russell discuss these 5 requirements in more detail in the introduction on pages 80 to 83. Thus we see that in the system of Principia Mathematica there can be no classes which are not determined by some suitable propositional function, and this is suggested by the comment on page 196. The characteristics of a class are that it consists of all of the terms satisfying some propositional function. Indeed, as we'll see, any class can be obtained just by considering predicative functions. The main definition of chapter 20 is definition 20.01, which is as shown on the screen. And there are some quite subtle aspects to this definition that I'll spend some time trying to explain to the best of my understanding. After all, Whitehead and Russell are not always the easiest to interpret, but I'll give it my best shot. So on page 197 we read, here f of the class determined by psi is in reality a function of psi blank. This comment needs some explanation, or at least initially I found this comment a little bit confusing and I want to spend some time explaining my understanding of it. If you're interested, then page 76 onwards of the introduction provides further detail on what I'm about to say. So up to this point, an expression such as phi blank has been interpreted as meaning a fixed function. But in the comment just quoted, the authors claim that f of the class determined by psi is a function of psi blank. And it seems to me that in this context the authors do intend the symbol psi blank to be interpreted as a variable which ranges over functions. However, this variable, psi blank, does not range over only predicative functions of a particular type. It does in fact range over predicative and non-predicative functions of different orders, but nevertheless, all of the functions in its range do have some things in common. Firstly, the type of arguments that they accept, and secondly, they are all formally equivalent. Therefore, For example, psi blank may range over all functions which have a single variable ranging over individuals, and this includes the first order matrices, predicative functions, second order functions, third order functions, and so on. Therefore, psi blank is not a variable in the usual sense that we've come to understand variable in Principia Mathematica, where usually a variable which ranges over a type of function will be thought of as ranging over a single type, usually a type of predicative function. But the variable psi blank seems to differ. The problem that we initially have is that a class can be determined by many different functions. What we don't know initially is whether all of the classes that we need are obtainable from predicative functions alone. It may be that predicative functions only account for some of the classes, and that there may be some classes which we do need to consider at some point, which can only be obtained from non-predicative functions. This, fortunately, is not the case. All classes can be obtained from predicative functions, as we'll see in the present chapter. The variable psi ranges over formally equivalent functions of potentially different types. If therefore for the time being we restrict the values of psi to one particular type, then we have a function f sub 1 psi blank, and this function will have a certain symbolic form. However, if we now consider psi blank as ranging over some other type of function, these functions are of course formally equivalent to the functions in the first type that we considered, then there is a function f sub 2 psi blank which is symbolically identical to f sub 1 psi blank. This is a consequence of the systematic ambiguity of logical connectives and so on. Therefore, even though disjunction, logical product, implication, etc. all have slightly different meanings for different types, we still use the same symbols to represent these closely aligned notions. And therefore we can see that on each separate type of function which psi blank ranges over, there's a function on each type which is symbolically identical to f sub 1 psi blank. Therefore, we simply consider the function f psi blank, which is effectively the collection of all of these separate functions together. F has a symbolic form which doesn't change as we pass from one type to another because of systematic ambiguity. However, as we pass from one type to another, in a very subtle way, we also transition from one function to another, even though the symbolic form doesn't change. Fortunately, we have the axiom of reducibility, which says that there's always a predicative function which is formally equivalent to any given function, and therefore our variable psi must also include some predicative functions in its range, and therefore our function f must be defined for some predicative functions. Therefore, again, in a very subtle way, the f which appears on the left-hand side of the definition 20.01 is potentially slightly different to the one on the right-hand side. Although they are symbolically the same, the one on the right-hand side has a variable which ranges only over predicative functions. And moreover, whenever the function f of phi exclamation mark blank is true, respectively false, then the function f of the class determined by psi is true, respectively false. And so the function f of psi blank, and hence also f of the class determined by psi, depends only on the extension of its argument. Therefore, it's an extensional function. We see on page 197, when a function phi exclamation mark blank is extensional, it may be regarded as being about the class determined by phi exclamation mark blank, since its truth value remains unchanged so long as the class is unchanged. Hence we require, for the theory of classes, a method of obtaining an extensional function from any given function of a function. This is effected by the following definition, which is definition 20.01. And we also read on page 78, by means of our derived function, we've practically removed the necessity for considering differences of type among functions whose arguments are of the same type. Notice that the authors say that we've practically removed the necessity, not necessarily the theoretical necessity. So we haven't completely got rid of non-predicative functions. They're still there, and they can still form classes, but we have a way of taking that information and expressing it in terms of predicative functions. And it isn't a problem to have functions with variables ranging over a type of non-predicative function. It's just that in Principia Mathematica, especially when we want to consider apparent variables, then we tend to only consider apparent variables which correspond to a type of predicative function or individuals. We don't bother with apparent variables which corresponds to variables ranging over types of non-predicative functions. Nevertheless, if we did want to have an apparent variable ranging over a type of non-predicative function, then provided that it formed a legitimate totality, then we could do this. We don't do it, generally speaking, simply because there's no need to. Everything that we need is accounted for by predicative functions. It may take a bit of time for the authors to set up the right definitions and propositions. We can't just assume from the outset that predicative functions account for everything, but eventually we end up at a point where non-predicative functions, though still there in the background, can safely be either completely or in large part ignored. And I think this would be a good time for me to just say a little bit more about non-predicative functions, just in case there's any misunderstandings. There is a distinction to be made between non-predicative functions and so-called impredicative functions. They're not the same things. Non-predicative functions are just functions that we've decided we do not want to define as predicative for whatever reason. Maybe it would be inconvenient to do so. However, it's entirely conceivable that certain non-predicative functions could reasonably be called predicative in some sets of circumstances. But on the other hand, impredicative functions are functions which are effectively defined in terms of themselves. Arguably, it's these types of functions that the authors of Principia Mathematica work so hard to banish from the system of Principia Mathematica. Non-predicative functions are not functions defined in terms of themselves and need not be banished. Because of the way that the system of Principia Mathematica is constructed, impredicative functions don't appear. The axiom of reducibility guarantees that there's always a predicative function which is formally equivalent to a given function. This doesn't guarantee that the two functions, which may be of different orders and usually will be of different orders, will each have the same symbolic form. It merely guarantees agreement on all values of their arguments. On page 75 of the introduction we see the symbols for classes, like those for descriptions, are in our system incomplete symbols. The uses of such symbols are so defined that when the definiens is substituted for the definiendum, there no longer remains any symbol which could be supposed to represent a class. Thus classes, so far as we introduce them, are merely symbolic or linguistic conveniences, not genuine objects as their members are if they are individuals. As we see in this definition, the incomplete symbol representing a class, z hat psi z, appears only in the definiendum and is completely absent from the definiens. Therefore, we must see f of the class determined by psi as a kind of abbreviation. And therefore, as with descriptions, for many of the demonstrations of the propositions of this section, it will initially be a case of replacing any propositions involving symbols representing classes with the equivalent proposition which doesn't include any symbols representing classes. And once this is done, we can apply without hesitation the results from previous sections, since we're just then dealing with propositions and propositional functions. As we've seen in chapter 14, descriptions and indeed incomplete symbols generally have a corresponding scope. The scope of the class symbols is not something that we really have to consider too much. However, if it is ever necessary to consider the scopes of any class symbols, they follow the same kinds of conventions as the scopes for descriptions. Those which appear in a proposition typographically first have the larger scope. Definition 20.02, shown on the screen, seems strange at first glance because in the definiendum we have something like x is an element of the predicative function phi exclamation mark blank. However, this is not so strange when we remember that the classes that we deal with in the system of Principia Mathematica are defined in terms of propositional functions. We don't assume that there are any objects called classes. Of course, if we think of the membership symbol as meaning what we usually consider it to mean in contemporary set theory, then we might struggle to make sense of its use here. And I reiterate that it's important to understand that when Whitehead and Russell were writing Principia Mathematica, what we might think of as obvious in contemporary set theory was still far from obvious to mathematicians and logicians at the time. Definition 20.02 applies only to predicative functions, but the use of the membership symbol will later in this chapter be extended, and its interpretation and typical use will more closely resemble its use in modern set theory. This definition is just setting things up for when we get to that point. On page 197, for example, we read, in this form, the definition 20.02, is never used. It's introduced for the sake of the proposition, that proposition which I've shown on the screen, which is one of the lines in the demonstration of proposition 20.3. And on page 82, this definition is only needed in order to give meaning to the expression X is a member of the class determined by phi. So now let's have a look at 20.03. We're told on page 198, the following definition defines what is meant by a class. In informal language then, definition 20.03 tells us that a class is one of those objects, alpha, for which there exists a predicative function such that alpha is equal to the collection of those objects which satisfy the predicative function. CLS, class, is the class of all classes of a particular type, and therefore CLS must be a class of a different type to those classes which are its elements. More will be said about types of classes later in this video. The definitions 20.04, 05 and 06 do not tell us how to interpret the membership symbol. They're just notational shorthand. Also, it's worth noting that the class symbols alpha, beta, etc. are used when it's not necessary or important to specify the defining propositional function of the class. Nevertheless, every class symbol can be replaced by a symbol of the form z hat phi z, if necessary. It's also worth noting that definitions 20.07 and 20.071, which tell us how to interpret apparent variables which range over, evidently, some type of classes. However, in the definitions of each of these definitions, we see that an apparent variable which ranges over some type of classes is really an apparent variable ranging over some type of predicative function. And these definitions will be critical to establishing the relevant formal properties of apparent variables which range over classes, and which will allow us to directly apply the results of chapters 9 to 14 to propositions with apparent variables ranging over classes. Being able to deal directly with apparent variables ranging over classes will be a big help, because as the propositions involving classes become more complicated, the corresponding propositions involving only propositional functions become practically unmanageable. Note that sometimes when a demonstration is omitted for a proposition that involves class symbols, that the hints that are given are often propositions that may need to be applied to the resulting expression when the class symbols have been eliminated, rather than directly to the proposition containing the class symbols. This won't always be the case though. Sometimes it's possible to apply the propositions directly to the expressions containing the class symbols, or to the equivalent proposition with the class symbols eliminated. So I'm just going to pick out and comment on some of the more important propositions in this chapter. 20.11. The truth value of a function of a class does not depend on whether we consider the class to be determined by one or the other of two formally equivalent functions. 20.111. If f and g are formally equivalent functions when considered as functions of functions, then this implies that they are formally equivalent when considered as functions of classes. 20.112. This is a class version of the axiom of reducibility, and there'll be more versions later in this chapter. 20.7, 701, 702, and 703. 20.13. Formally equivalent functions imply that the classes that they each determine are equal. 20.14. If the classes determined by two functions are equal, then the functions must be formally equivalent. And 20.15 is just 20.13 and 20.14 combined to make an equivalence. 20.151. Every class determined by some function psi is equal to a class determined by some predicative function. This is an important proposition from which we can define the type of a class. On page 198 we read, alpha is of the type next above that of z, and CLS is of the next type above that of alpha. Every class can be defined by a predicative function. There are no classes which cannot be defined by a predicative function. Therefore, since predicative functions form a legitimate totality, then we have, as we see on page 79, the totality of classes to which a given term can be significantly said to belong or not belong is a legitimate totality, although the totality of functions which a given term can be significantly said to satisfy or not satisfy is not a legitimate totality. The type of a class does not depend on the type of the defining propositional function, and depends only on the type of the objects which are the elements of that class. That is, the type of the objects which are arguments in any of the defining propositional functions, since, as we see, we can always find a suitable predicative function which defines the class, and a predicative function always has an order which is one above the greatest order which appears amongst its arguments. Therefore, the hierarchy of types of classes would appear to have a much simpler structure than the hierarchy of functions. On page 31 of the introduction we see there are no classes which contain objects of more than one type. Proposition 20.18, if two classes are equal, then the truth value of a function f, considered as a function of classes, does not depend on which class we choose as the argument. Propositions 20.2, .21 and .22 show that equality of classes forms what we might call an equivalence relation, and we're told on page 198 that equality between classes is defined by applying 13.01 symbolically unchanged to their defining functions and then using 20.01. 20.23, .24 and 25 are alternate forms for transitivity. And 20.3, if an object is an element of a class, then that object satisfies the function which determines the class. This proposition, of course, tells us more generally what it means for an object to be a member of a class. The membership symbol has not been used in this chapter up to this point, except in certain definitions at the start of the chapter. Note that the expression x is a member of the class determined by psi is to be considered as a function of the class determined by psi. That is, x is a member of the class determined by psi is to be considered as something of the form f of the class determined by psi, in which case we can apply proposition 20.1 and subsequently we can see why we need definition 20.02. Proposition 20.31, notice that the expressions x is a member of the class determined by psi and x is a member of the class determined by chi are propositional functions. Thus, if two classes are equal, then whatever is a member of one class must be a member of the other class. This proposition says then that, as written on page 26, a class is wholly determinate when its membership is known. That is, there cannot be two different classes having the same membership. 20.43 is another formulation of 20.31 but using class symbols. Proposition 20.34, x equals y, then whichever class x is a member of, y must also be a member of that class. Propositions 20.5 to 20.59 are propositions which involve both classes and descriptions. I'm going to skip over these here. It's not that these propositions are not important, they are, especially when it comes to section D onwards, which deals with descriptive functions and classes of reference and classes of relata. It's just, I don't have much to add about these propositions to what's already there in Principia Mathematica. From 20.6 onwards, we've got some very important propositions which allow us to formally apply any proposition from chapters 10 to 14 using class symbols as apparent variables without having to constantly rewrite using the definitions 20.07 and .071, etc. Of course, as you look through chapter 20, you can see that class symbols have been used already as apparent variables. For example, 20.54, 20.25 and 20.34 to name some. But notice also that the class symbol had to be eliminated in the demonstration. With the propositions from 20.6 onwards, this rewriting becomes unnecessary. On page 209 we read, "From the above propositions it appears that although expressions such as the class determined by phi have no meaning in isolation, yet those of their formal properties with which we've been hitherto concerned are the same as the corresponding properties of symbols which have meaning in isolation. Hence nothing in the apparatus hitherto introduced requires us to determine whether a given symbol stands for a class or not, unless the symbol occurs in a way in which only a class can occur significantly. This is an important result which enables us to give much greater generality to our propositions than would otherwise be possible." We also read on page 198 the use of single letters in place of such symbols as z hat phi z or z hat phi exclamation mark z is practically indispensable, since otherwise the notation rapidly becomes intolerably cumbrous. And I concur. When I get round to making a video for chapter 22, then I may give an example of a demonstration which in Principia Mathematica uses class symbols, but then give a separate version which eliminates the class symbols. Proposition 20.8, the antecedent will be true only when phi blank is significant for the argument A. And recall that a propositional function is significant for a particular argument if phi A is either true or false and not simply a meaningless string of symbols. And in this case, the class determined by the propositional function phi x or not phi x has identity with the class determined by the propositional function x equals A or x is not equal to A. Proposition 20.81 shows that if two functions phi and psi are significant for the same argument, then the class determined by the range of significance of phi has identity with the class determined by the range of significance of psi. Moreover, the class that's determined by each of these propositional functions will contain all objects of a certain type. If a propositional function is significant for one value of a certain type, then the propositional function is significant for all values of that type. And on page 210 we read, since a type is the range of significance of a function, if phi x is a function which is always true, the class determined by phi must be a type. And, in virtue of 20.8, if phi a is significant, the type to which a belongs is the class of arguments for which phi x is significant, i.e. the class determined by the propositional function phi x or not phi x. And if there is an argument a for which phi a and psi a are both significant, then the class determined by phi and the class determined by psi have the same range of significance in virtue of 20.81. So I think that's about enough for chapter 20, so let's move on to chapter 21, the general theory of relations. Chapter 21 introduces the concept of a relation, and on page 27 we see any function phi xy determines a relation R between x and y. As with classes, relations are to be understood in extension. On page 27 of the introduction we also read, relations like classes are to be taken in extension, i.e. if R and S are relations which hold between the same pairs of terms, R and S are to be identical. Relations can be considered as classes of ordered pairs, x, y, and it's important to distinguish this pair, or couple, from the class containing x and y, since the class containing x and y does not have sense, whereas the ordered couple does have sense. This, however, is an informal interpretation of relations, and thus we don't need to take ordered pairs as a kind of primitive notion. On page 27 we see, if we regard a relation as a class of couples, the relation determined by phi xy is the class of couples xy for which phi xy is true. Whitehead and Russell discuss in more detail the interpretation of relations as classes of couples on page 27 of the introduction. I won't say any more about it in this video. xRy is a propositional function said x has the relation R to y. As with classes, where the symbols alpha, beta, etc. may be used to represent classes, particularly when the defining function is not important, Whitehead and Russell use the symbols R, S, etc. to represent relations, where the defining function is, again, not important. However, when it is important to make clear what the defining propositional function is, we see on page 27, the relation determined by the function phi xy will be denoted by phi hat y hat phi xy. The propositions concerning relations are so similar to the propositions concerning classes that I'll follow Whitehead and Russell's example and not spend a great deal of time on them. The definitions from this chapter are shown on the screen now, and the only one that I'll spend a bit of time discussing is 20.02. There's a substitution convention that the authors introduce on page 211. If you want to read it, then it's on the screen now. However, I'll try to summarise what they say using examples that they give on page 112. As can be seen, there are letters A and B without circumflexes and letters X and Y with circumflexes. For the letters with circumflexes, we consider them in their usual alphabetical order, so of course X precedes Y in the alphabet. The letters A and B we consider in the order in which they're mentioned in the written form of the expression, their typographical order. Whichever letter A or B is mentioned first will be substituted for the X with a circumflex. Whichever letter A or B is mentioned second will be substituted for Y. So in the first and third examples, we see A is mentioned first and B second. So A will replace the x with a circumflex, and B will replace the y with a circumflex, irrespective of the order of x and y in the expression. In the second and fourth examples, B is mentioned first and A second. So B replaces the x with a circumflex, and A replaces the y with a circumflex, again, irrespective of the order of x and y in the expression. What, you might ask, would happen if other symbols were used instead of x's and y's and a's and b's? Well, I'm not going to worry too much about this, to be honest with you. If I ever feel that I need to worry about it, then I'll worry about it. So moving on, notice that 21.02 is comparable to 20.02 in that what is defined is effectively what it means for the pair of arguments a and b to be a member of the propositional function phi exclamation mark blank blank. The more useful notion of what it means for a pair of arguments to be a member of a relation is given in the proposition 21.3. And there's very little for me to say about relations. Section 21 relating to the theory of relations almost exactly mirrors the section 20 relating to the theory of classes. As with chapter 20, some of the propositions from this chapter, namely propositions 21.6 onwards, show that the relation symbols, which have no meaning in isolation, have all of the same formal properties of those symbols which represent objects which do have meaning in isolation. So all of the propositions from chapters 10 to 14 can be formally applied to propositions which involve relation symbols without first having to eliminate the relation symbols. So that brings us to the end of chapters 20 and 21 and to the end of this video. If there's anything that you'd like to ask about this video or any other video on my channel, then please feel free to get in touch. Please remember to subscribe and hit the like button to show your support, and share this video with anyone that you think might be interested. Thank you for watching.